Okay, so one of the things is, and there's an assignment A, B, C, and D actually in this part 3. Believe it or not. Yep. So, yeah. So my point was going to be that what you guys handed in was.
So those are A and B.
Right. This will be C, and then there's one that's D. So the problems that you guys did were clearly weak acids. So I'm looking forward to reading those. Now we're switching gears, and we're going on to weak bases. So one of the things clear back in part 1 in this unit, you guys had to tell me, would this be a better acid or would this be a better base? Would this donate a proton or would this accept a proton? Acids donate protons, bases accept protons. I'm just mentioning that because now actually we're segueing to weak bases. Okay? So let's calculate the hydroxide ion concentration and the pH if you have a 0.10 molar solution of the acetate ion. So can you see how the acetate ion would act like a base? Bases accept protons. Doesn't it look like it just wants to accept a proton?
Yeah.
So, thank you. And so it's kind of like we have this pattern here. You're going to want to write the equilibrium, write the Kb expression, and go ahead and work an ice table. Those 3 things. Equilibrium. Yep, it's the same thing. Equilibrium, Kb expression, ice table. Okay. So here we go. This, you'd have to recognize it's a weak base. Okay? And so here's how it acts as a weak base. The acetate ion, CH3COO negative, that's the acetate. Sometimes it's written CH3CO2 negative, will hydrolyze a water molecule, break it apart. One of those covalent bonds between the oxygen and hydrogen. And it will then pick up the H+. It sucks on the H+. Notice that actually we're going to call these conjugate acid-base pairs here in the next part. The CHO, the CH3COO, and the CH3COOH are different by a hydrogen. They have a proton. And then also it releases the hydrogen ion. Excuse me, the hydroxide ion, the OH minus. And so, of course, the 2 things you're supposed to get, the hydroxide ion in this case, and the pH. So I would write the Kb expression. It's the molar concentration of the products, which would be the protonated acetate, CH3COOH, times the molar concentration of the hydroxide ion, divided by the molar concentration of the acetate ion. And you can look that, so that 5.6 times 10 to the negative 10th, that would be potentially on a table. All right. So I can't remember. I did one of these in my notes. Is this one I did in my notes? Nope, I didn't do this in my notes. Okay, so I didn't do an ice table. And now I remember, I was sitting at my desk and I'm like, I don't need to do an ice table. Okay, just picture your ice table. I know, we have an ice table coming up on the next slide. So I would actually have 3 columns. I would have the acetate ion. The acetate ion with a proton actually is called acetic acid. That's the CH3COOH. And then I would have 1 column for the hydroxide ion. And the first row is always the initial concentration. Okay, and of course that would be 0.10 molar for the acetate ion, zip and zip for the other 2. And if we let X, the change, be equal to the amount of acetate that's going to hydrolyze, we'll have a negative X there, a positive X, and a positive X under the other 2 columns. So at equilibrium then, here are your equilibrium concentrations. This is that 3rd row. You're going to see on the ice table here in a minute. So the acetate ion in the 3rd row is going to be what it started out with, minus X. And so, yeah, we're going to go with a simplifying assumption again. So here's your ice table. Okay. So like I said, what I've been doing is I like to draw a line here that says basically you take initial, add the change, and get the equilibrium concentrations. All right. So if we plugged back into your Kb expression, it would look like this, where we have the acetic acid as X, The hydroxide ion is X. The acetate is 0.10 minus X. And that's equal to your Kb. So that's that constant that you look up. So simplifying assumption, if the amount that hydrolyzes, if X is really small compared to 0.10, then actually the equilibrium concentration of acetate, 0.10 minus X, is essentially equal to 0.10. And things fall into place. And you might be wondering, when can you apply a simplifying assumption? And the deal is that the molar concentration needs to be significantly or a little bit larger than your Kb. So here it goes. In general, if the molar concentration of your, in this case, acetate ion, your weak base, if it's greater than 100 times your Kb, you're probably okay. So of course our Kb up here is 5.6 times 10 to the negative 10th. So you're looking at, it has to be at least 5.6 times 10 to the negative 8, then you'll be okay. Okay, and it is clearly larger than that. It's 0.1. So we're okay. So applying our simplifying assumption, in the denominator, it goes from 0.10 minus X to 0.10. Okay, and this is definitely solvable. So I kind of usually think of kind of crisscrossing and then taking the square root of both sides. So basically, if we take the square root of 5.6 times 10 to the negative 11th, that will be our value for X. And the reason I like using the ice table is if you're like, well, what's X? Well, X is the hydroxide ion concentration, right? If you look back at your table. So square root of that number, you get 7.5 times 10 to the minus 6th. And this is where on some of your papers I put M. Do not forget that this is molarity. I think it's easy to kind of lose track of putting units when the Kas have no units. The Kas, Kcs, Kps, yeah, definitely. So then the other part of this problem was to get to pH. We can do that a couple different ways. Oh, by the way, if you were not to apply the simplifying assumption and have to use the quadratic, you would get an exact solution of also 7.5 times 10 to the negative 6th. So that's good, in case you were worried. So we need to go from that hydroxide ion concentration to pH. One way to do it is to go for the hydrogen ion concentration first. So we know that the product of the hydroxide ion and the hydrogen ion is the Kw, 1.008 or 1.01 or 1.0 times 10 to the negative 14th. So rearranging that, solving for your hydrogen ion concentration, your hydrogen ion concentration is equal to 1.0 times 10 to the negative 14th divided by your hydroxide ion concentration. So if we plug in our hydroxide ion concentration and go ahead and divide it out, you know, molar concentration of the hydrogen ion is 1.0 times 10 to the minus 14th, divided by 7.5 times 10 to the negative 6th, which is equal to 1.3 times 10 to the negative 9th moles per liter. 1.3 times 10 to the negative 9th moles per liter. And we're almost done. So to get pH, we need to take the negative log of that. And if we do that, rounding it to two significant figures, right? Okay, you get 8.87. Two significant figures. When you apply the log function, or excuse me, apply the p function, or take the log of anything, your significant figures are after the decimal right here. Okay, any questions? Just looking for. All right. Very good. Here's your homework. Did you have homework handed?
Yeah, I had a question on this one.
Okay, very good. Well, let's take a look at these, shall we? Okay. So these are all going to be, these are all going to be weak bases. To work these problems in general, you're going to write the equilibrium, and then you're going to write the Kb expression, then you're going to write the ice table. That's how I would do them. They're easier to grade that way. And then you're going to solve for whatever you need to solve for. And oftentimes under solving, you are going to have to apply a simplifying assumption. Use simp assump. And state that that's what you're doing. All right, so let's take a look at these. Okay. Oh, that wasn't it. It's like, that doesn't look familiar. Here, this is better. Okay. So, what must the molarity of an aqueous solution of trimethylamine, CH3, quantity 3N, be if it has a pH of 11.12? Okay, now we know from pH we get the hydrogen ion concentration, right? So one of the things I told you to write the equilibrium, so actually the equilibrium is already given in your problem. We're showing it hydrolyzing water and picking up a proton. So if you compare either side of the reaction arrow, okay, there is actually your what we're going to call conjugate acid-base pairs. It's picking up a proton. How do you know we have an extra H? H plus. So the other thing I told you was to go ahead and write the Kb expression. And of course it would look like this. The hydroxide ion times that thing with an H plus divided by the amine thing that you started out with. That's your Kb expression. Do the ice table. That's all this is. You know, kind of get used to drawing those things that differ by a proton. Okay. So here's our ice table. Don't let the stoichiometry throw you off. It's not always a 1 to 1 to 1 to 1 to 1 to 1 like it is here. But here it is also again. So we have a negative X for our weak base, a plus X for our, with a proton on the other side, and a plus X for our hydroxide ion. So the thing we want to solve for is the initial molar concentration of the weak base. So here's the deal. I bet you're good with this. If we go back to that pH, we can get to the hydroxide ion. And that hydroxide ion actually is the equilibrium concentration right there. So if you got that, then you have X. Okay? So if you have X, then you can go ahead and plug in those what the real number is. Now, I don't know what X is. You know, I could like maybe look at the answer key, but you guys find X, it'll be a real number. So actually, instead of X's, you'll have real numbers here. Now, we've really been into applying the simplifying assumption. So if we say X is very small compared to that, and that's what we're trying to get to, okay? And I kind of put it the other way around, okay? If this is pretty large compared to X, I just turned it around, then basically, no pun intended, our equilibrium concentration is equal to our initial concentration. So anyway, if that's the case, then we can revisit our Kb expression and go ahead and plug in like we've been doing. Remember, X you really know, okay? So we have this number we know, this number we know. This is from, actually it was given in the problem this time, but a lot of times you can look it up on the table, and we're solving for the initial concentration of the weak base, which is well, that makes sense, trimethylamine. All right, so that's that one. The next one, and I didn't give as much details, I just said write the equilibrium and the Kb expression. Okay, I went ahead and wrote the equilibrium for you. So always with a base, it's going to accept a proton from a water molecule and leave hydroxide as the product side. So you're going to need to look up the Kb value for CH3NH2. I looked it up, so that means you can look it up. Okay. And then once this is the equilibrium, there's the Kb expression. You still need ice table, solve for the equilibrium concentrations. And here they want the hydroxide ion, the hydronium or hydrogen cation, pH and POH. Knock them out. Next one. This one, I guess a catch is they give you the saturation amount of this particular weak base in grams of solute per 100 grams of, for 590 grams of solvent, which is water. So you're going to have to break out those Chem 1 skills and knock that into moles per liter. My hint is you're going to have to use the density of water. I think at some point, density of water, go with 1.0 times 1.0 grams per milliliter. Times 10 to the, no. Okay. So you'll get that from saturation information. Right, Kb expression, they went ahead and gave you the equilibrium. Make the ice table. Don't forget to apply your simplifying assumption. And then you can get the hydroxide ion concentration from your equilibrium. And then you can get pH from the hydroxide ion concentration. Last one is kind of like the last one that you did for today's homework, where it asked for the degree of ionization. But let's not worry about that for now. Basically, again, no pun intended, we have another proton acceptor. So it accepts a proton to form what? C2H5NH3 plus, right? So write the equilibrium, write the Kb expression. You can look up Kb. Prepare an ice table. Apply a simplifying assumption. And then get equilibrium concentrations. So for A, whenever it asks for percent of ionization, basically it's the amount that you get on the product side divided by the amount that you start with. So in this case, it's the amount of the conjugate, we're going to call it conjugate acid, the protonated version of the weak base, divided by the weak base that you started with. Percent ionization is that times 100. That's that. All right. On to something different. One more topic. So this would be D, okay, in part 3. So we already talked about this idea that you can have an acid kick off more than one proton. Polyprotic acids definitely happen. They kick off 2 or more protons. Amphiprotic is one that can actually accept a proton as a base or can kick off a proton like an acid. So if you do have something that can kick off more than one proton, you'll have a Ka for each time it kicks off a proton. So, but the first proton to go is the easiest and so has the highest Ka, and then the Kas, those ionization constants, get smaller after the first one. Okay? So if you do have, and we're gonna talk about sulfuric acid here in a minute. So if you do have something like H2SO4 that can kick off 2 protons, okay, basically I keep saying basically today, and that makes me laugh because we're talking about acids and bases. So if it can kick off more than one hydrogen, basically its acidity of the solution is driven just by that first ionization. And we're going to kind of prove that with this one. Was it 6? I think it was 6 strong acids you're supposed to memorize, and sulfuric is one of those strong acids. Okay, but when we talk about being polyprotic, okay, I don't think my notes kind of scream this. Maybe they do. I guess they do. But when we talk about sulfuric acid being a strong acid, of course we use one-way arrows. Okay, so it kicks off one of those protons and it leaves behind this. Okay, that's the first ionization. The second ionization takes this guy, okay, and does it again. It being kicks off a proton. Okay, so if this is going to kick off a proton, that leaves us with the sulfate ion. Okay, so this is strong, this is weak. Okay, that's kind of what we're talking about, polyprotic acid. Oops, guess what? Is that better? So that's kind of what we're talking about here. So in this problem, we're given a 0.1 molar solution of H2SO4. Since it's strong, you buy that. Since it's strong, that's what we got going on. So now in our calculations it says determine the pH of this solution, okay, by considering the H plus that's generated from both ionizations. So in order to get to this one, we need to consider this weak acid, and we're going to just do it just like we did with other weak acids. So do you see where actually the initial concentration of this HSO4 is 0.10 molar? Okay, and that came actually from the complete ionization of the strong acid. So this is what that looks like. So actually this on this slide is this that I kind of put up over there. So we have the first ionization of the strong acid, okay, and then we have the degree of a certain amount of ionization in equilibrium. HSO4 is acting as a weak acid. It's a pretty strong weak acid though. Remember, the higher the Ka, okay, the more it favors the product side. That's pretty high. Okay, so here we go. Oh, by the way, and I don't know if there's a typo in yours. There was in my notes I've been using. Let's find sulfuric acid. And these are the Kas that we're using, where that one is, of course, 0.011 is that Ka. Okay. So, yeah, from the first ionization, strong acid, the molar concentration of your hydrogen ion is 0.10. Okay. So in order to come up with this equilibrium concentration, we need to recognize, remember we talked about the common ion effect, we need to recognize that we do have a significant amount of hydrogen ion already there. So on our ice table, and actually I did make an ice table of this, on our ice table for this equilibrium, we are going to have to put in not 0 for the initial concentration of hydrogen ion, but 0.10. So now here, I think I can go ahead and bring in that thing I was going to do before. Okay. So on the next slide, does that look right? Thanks. Yeah, that is where I want that. Cool. Okay. So just focusing on the second ionization, it looks like this. That's the equilibrium, and of course the Ka expression is the hydrogen ion times the sulfate cation divided by the bisulfate cation. And the Ka we got from the table. Oh, see, now there's my typo. I told you there was a typo here. Sorry, 0.011 is the Ka from the table. All right, so here is my ice table. We have 3 columns. Initial change and at equilibrium. We said the initial of the HSO4 minus is 0.1 molar. The initial of the hydrogen ion is also 0.10 molar. The initial of the sulfate ion, zip. It's like you're keeping score. So with regard to change, we have kind of our usual change. The stoichiometry is the 1 to 1 to 1. So we have a minus X for our HSO4, a plus X for our H, and a plus X for our sulfate. And so we know to get equilibrium concentrations, we take the initial and apply the change. So for the HSO4, it's 0.10 minus X. Okay, so for the H plus, it's 0.10 plus X. It's kind of weird. For the sulfate, it's just simply X. So let's take a look at the simplifying assumption. If X is a lot smaller than our 0.1, okay, then actually both of these things both of these things, if x is very small, they become 0.1. Isn't that not cool or what? If x is very small, then 0.1 minus x is approximately equal to 0.10. 0.10 plus x is approximately equal to 0.10. And if you think this is going to be an interesting thing when you plug it back into the Ka expression, it kind of is. So with all that in mind, is that right? Maybe I don't. No, I have one more build. Okay. So plugging back into the Ka expression, Ka is the molar concentration of the hydrogen ion, 0.10, because the x didn't mean anything, times the molar concentration of the sulfate, which is x, divided by the molar concentration of the HSO4 minus, which is also 0.10. So these things cancel, right? 0.10 cancel, and we get x is equal to Ka, which, yeah, that is a typo again, darn it. That should be 0.011. So that's x. And what was x? X was the amount of extra hydrogen ions you'll get. X was also the amount of sulfate you'll have formed. Okay, so this actually is kind of, I like the ice table. This is basically a flattened ice table. Okay, it's saying, what sort of changes do you have going on? Well, if we let x be equal to the moles of HSO4 that's going to ionize, that's also equal to the moles of H plus that will be formed, and the moles of the moles of sulfate that will also be formed. And then you recognize that last set of stuff is our bottom row on our ice table. Okay, so and this kind of comes to the same conclusion I had on my table, that if you apply the simplifying assumption, basically your 0.1 and your 0.1 will cancel out, and you'll be left with x is equal to Ka, or x is equal to that 0.011. Now, if you take, how's this go? We said if you take 100 times your Ka, so 100 times Ka, 100 times 0.011 is 1.1, right? So actually, our simplifying assumption is, I'm never going to make you not, I know, I'm never going to give you a problem where you can't go with the simplifying assumption, but we're kind of outside the rules here, aren't we? Because 0.1 is not greater than 1.1. Okay. In fact, I go ahead and I tell you, if you were to apply the quadratic, instead of getting 0.011, you could get 0.0092. Okay. But it's a good example. That's why I went with it. Okay. But you're going to see, actually, after you round, it wouldn't make a difference. So what this problem wanted you to do was basically take the molar concentration you get from the first ionization, 0.10, and then consider the second ionization, the exact solution is 0.0092. Okay, add them together. So the whole hydrogen ion concentration, including the effect of the common ion, would be actually rounded to 2 decimals, because that's all we have in our initial molar concentration of from our first ionization. It rounds to 0.11, which is the same number you would get if you went with the 0.011 molar as a hydrogen ion concentration with the second ionization. So that's it. Almost done. So that's the hydrogen ion concentration. We're supposed to knock out the pH, and we know how to do that, right? So that would be take the negative log of 0.11, and you get 0.96. If you were just to go with the ionization from the first ionization, if you take the negative log of 0.10, you get 1.00. Okay? So, in other words, we bumped it, 0.04 units on the pH scale. But moving around on the pH scale is not linear. It's a logarithmic scale. So that's significant. So those are the 2 pHs. The 0.96, if you consider both ionizations 1.00 if you only consider the first one. All right, now on to the problem. Oh, I guess more slides. Okay. So let's take a look at this one. Notice the special instructions, because the problem I'm going to show you, number 48, does not ask you to come up with a pH, but I'm asking you to throw in the pH. You're already almost there. So also want the pH of this solution. So this is what it looks like. D. Okay. So polyprotic, H2CO3 can kick off 2 hydrogens. That's kind of what we got going on. Okay. So you're supposed to ultimately calculate, this is after both ionizations, calculate how much H plus you have, H3O plus, same thing, and then those other 2 species. So this, I'm showing you the first ionization here. Okay, the second ionization takes the HCO3 and kicks that hydrogen off. So it looks like this. Okay, and I went ahead and wrote the Ka expressions for both of them. So my suggestion is going to be very, have some similarities to the sulfuric acid problem we did. I would suggest 2 ice tables, 1 for each ionization, first and second. Don't forget the common ion effect for your second ice table. And then to get the overall, kind of do what we did here, you're going to add up the hydrogen ions from both ionizations. Yes?
Shouldn't the first one be in equilibrium? Since it's...
Yeah, I do have it in equilibrium. There's 2 arrows there.
Should it?
Yeah, it is. They're both weak.
Oh, they're both?
Mm-hmm. Yep. So that's where it is different than the sulfuric acid we did. Carbonic acid is weak. The first ionization is weak and the second ionization is weak. So you'll find a real value for Ka1 and a real value for Ka2. Yep. Good question, though. So for A, you'll add up these. Okay. For B, the HCO3 negative. So for B, to me, that will just be this equilibrium concentration here. Okay, I think. And for C, the equilibrium concentration of the carbonate once it's stripped off of two protons. And then don't forget, my other hint was also calculate the pH. Okay, so those are those 2. All right. Well, we need to forge ahead a little bit. I know. Like, oh my gosh. Yes, we do. But, for part 4, no kidding, the problems at the end, I don't know if we'll get clear to the problem slide, but for part 4, the problems are like, well, I'll show you. There's the same chapter, 5, 7, and 8. My point is that you've already been doing harder ones than these. I don't know. You don't look like really.
So we're going to get to that final slide, is that what you're saying?
I'm not sure. We might. This stuff does not take too long. And I've already been kind of alluding to the conjugate acid-base pair on either side of the equilibrium arrow. That's what this is. So I don't know. And I will not be distracted. I'm just kidding, kind of. Okay. So yeah, it's stuff you've already been doing. It's kind of fun. No, honestly, all kidding aside, I do need to use your time wisely, because we're kind of bumping up against a unit exam, and there is a Unit 5 set of stuff in here. It's over electrochemistry, so it's kind of fun. But it needs some time. There's no Unit 5 exam, but I need to allow enough time at the end. All right. So yeah, kind of from left to right, see it's subtracting a proton, so it's acting as an acid, right? If you were to go from right back to left again, that B minus, it's acting as a base. But I would say going from left to right, we would call this HB the acid, we would call B minus the conjugate base, acid-base pair, okay? They differ by a proton. If instead of going left to right, if we were going from right back to left again, and it seems like we did some of this clear back when we first started talking about acids and bases. If we were going from right back to left again, I would call B minus my proton acceptor, so I would call it a base, and I would call HB its conjugate acid. Honestly, a lot of times I don't know, I get confused which to put the word conjugate with, so I just go with conjugate acid-base pair. Okay, conjugate acid-base pair. So, a couple of examples, or some examples of conjugate acid-base pairs. Okay, and I think these are all going from left to right. So if H2O is donated proton, okay, it's the acid. After it donates a proton, OH minus is its base. Going from left to right, if H3O plus is going to, the hydronium cation is going to donate a proton, okay, it will be the acid. Once it loses its proton on the product side, it will be, the conjugate base will be H2O. Also going from left to right, sulfuric acid, like, dude, that equilibrium arrow, we were just kind of talking about that. That should not be there, but just bear with me. If this was a weak acid, we could make it we could make it, I think it's not sulfuric acid, but sulfonous acid, H2, let's do that one, that will be fine. H2SO3 was what I was going to say. We can fix that. Okay. It kicks off a proton, and we have HSO3 minus over here. That makes more sense. Conjugate acid-base pair. Some more, still going from left to right, HNO3. We can fix that one too, because that's also a strong. HNO2 has that. It's a weak acid, donates a proton. NO2 negative would be its conjugate base. NH4 plus, I can't remember. I think that is a weak acid. It donates an H plus. It turns into ammonia, ammonium cation and ammonia. Actually, those are conjugate acid-base pairs. And I'm tired of fixing things. Yes, HCl is a strong acid, so that should be one-way arrow. I'm trying to think. But even with a one-way arrow, I guess it still would. You would still have a pair, an acid-base pair. So to fix that one, hang on. I'm just going to make this into a one-way arrow. Let's fix that one. Okay. That's better. Okay, so on either side of the equilibrium arrow, usually an equilibrium arrow, you can pick out a conjugate acid-base pair. And for that, those things, you should be able to calculate a Ka for the acid and a Kb for the base, for that pair. And it's cool that if you multiply them together for that pair, they equal Kw. And Kw is that thing you're going to memorize, the 1.0 times 10 to the minus 14, right? Depending, that's 2 sig figs. So for any acid-base pair, I think that's awesome. So yeah, Kw is that 1.0 or 1.01 or 1.008 times 10 to the minus 14 at 25 degrees Celsius. And I have a little proof to kind of show you why that is. Okay, so if we switch gears to something generic, you know, the HB would be the weak acid and the B minus is its conjugate base. Okay, our conjugate acid-base pair, I like to kind of think of it that way. Then we can take the weak acid and show its ionization like this, okay, kicking off to form a proton, and the B minus, which now we know is the conjugate base of HB. The Ka expression would look like this, okay. For the conjugate base, we could show it hydrolyzing a water molecule, okay, acting as a base, taking a proton to form HB, okay. And as it hydrolyzes water, it forms the hydroxide ion on the product side. the Kb expression for that conjugate base would look like this. Now, the reason these two things are important is if this is 1, equation 1, if equilibrium 1, if this is equilibrium 2, one of the things we know is that we can add equations, and let's see what would look like, what would happen if we added these equations. Notice our HB's cancel, our B minuses cancel, and basically, oh, I'm so funny. I get basically, what we end up with is this. Okay? We have, if you add those two together, conjugate acid-base pair, you get the, this is the autoionization of water, water breaking apart. Okay? And we know that the autoionization of water is Kw. And we said that if you know the equilibrium constants for a couple of equilibrium, you add those equilibrium together to get an overall equilibrium of interest. I'll just put a star here since that's our overall equilibrium of interest. We know that actually we can, if we multiply these two together, we get the Kc of our equilibrium of interest. So that's kind of how that works. So kind of side by side, I've got the ionization constant for the weak acid, the hydrolysis constant, or Kb, for the weak base. They're here, okay? Then, if you're going to multiply them together, before you multiply, you might as well cancel terms that will cancel. Okay, again, your B minuses and your HBs cancel. And, of course, you end up with Ka times Kb for a given pair, conjugate acid-base pair, is equal to Kw, which is equal to the hydrogen ion concentration times the hydroxide ion concentration. That's what you guys have been using already, Kw. So that's just kind of a proof to hopefully prove to you that. All right. So before I go on, let's see. Let me show you when you'll use this. So let's just say, I'll just write it this way. Use this to get Ka or Kw, sorry, Ka or Kb if it's not on the table. Okay, and trust me, sometimes you need to do this for a test, sometimes you need to do this on problems. Sometimes for an acid-base pair, you're given Kb because it's more of a base than acid, but what you really need is Ka. So in order to get to it, you have to use this relationship. All right. This is the relationship you have to use. So since, like, multiplied together, they equal a constant, when one gets stronger, the other must get weaker. They must have an inverse relationship. So the stronger the acid, the greater the Ka, the stronger the Kb. Sorry, did I say it wrong? The stronger the Ka, the stronger the acid, the greater the Ka, the stronger the acid, the weaker the Kb, the weaker the acid. And vice versa for a given pair. See how pairs are so important? So this is a table we looked at before, I think. And if you look across a row, you'll kind of see the conjugate acid-base pairs. And like I said, I do just prefer just to kind of say conjugate acid-base pairs. And you can figure out which one is the acid, which is the conjugate acid, the base, the conjugate base. But no, not so surprising. So for instance, if we pick on the ammonium cation, you know, you go across, and they differ by a proton. You know, nitrous acid, is that one of them? Differ by a proton. So it's not usually too hard to look on either side of the reaction arrow or equilibrium arrow and to pick out the conjugate acid-base pairs. So this is a classic. This is a classic that we're going to wait until Monday. So it's a great problem because sometimes this sort of problem will end up on your unit exam.